Hi, NA Physics, it's Mr. Neff. Let's talk about the Doppler effect. Uh, Before we do, what was the problem with the boxing gym that only had one punching bag? I'll tell you at the end of the video. Found this nice simulator at lonkappa.org, and it will let you place an object that's producing sound, and you'll see that the sound moves out in all directions. Now, before the video, I timed the frequency of this. I put the pointer in a spot and I said 1, 2, 3, 4, 5, 6, and I timed for 10 cycles. And when I did that, I got 6.2 seconds for 10 cycles. You can try that for yourself and see if you agree. So if I have 6.2 seconds in 10 cycles, that gives me a frequency of 1.6 hertz. I just divided the 10 cycles by the 6.2 seconds. Now, I could have done that in the front. I could have done that in the back. And in either spot, in the front or in the back, if I did an observation, I get the same frequency. So if I put an observer in the front, if I put an observer in the back, they're going to make the same observation in terms of frequency. They're both going to say that 1.6 hertz is the frequency. Now, you say, well, of course, how can that be made any more difficult? Well, check this out. What if I took the source and instead of just letting it sit there, I let it move? And so say I did this. So now the source is producing waves on the same 1.6 hertz that it did before, but it's moving at the same time. And you can see that the wavelength in the front is shorter than you had last time, and the wavelength in the back is longer than you had last time. And if you're watching this carefully, let's start it again. If you're watching this carefully, you see that you get two different frequencies in the front and the back. Look, 1, 1, 1, 1, 1, 1, 1. That's pretty frequent. Versus back here, 1, 1, 1, 1, 1. That's a lot less frequent. And so it's not because the plane is making sounds any less frequently, but you're perceiving them less frequently because of the motion of the source. In a nutshell, that's called the Doppler effect. So now you can see that if I put an observer in the front of this and I put an observer in the back of this, this person in the front is going to perceive a frequency that's a lot higher than was produced, and the person in the back is going to hear a frequency that's a lot lower than what was produced. Again, this idea is the Doppler effect. That is, perceiving a frequency differently because of the motion of the source or the motion of the observer than was produced. So we're going to have 4 cases here. We're going to talk about when the source is moving, like we just saw in that video, and then we're going to talk about when the observer is moving. And those give you similar but slightly different effects. Let's talk about if the source is moving towards the observer. So if in that case, you can see in this picture, I have a fire truck. And the fire truck at rest is producing a wave and a wave. Sounds pretty fast, and so if the distance between compressions might be pretty far. Now, if the fire truck starts moving, the wavelength will be this altered wavelength. They're calling it wavelength prime in a picture. It's shortened by whatever the speed of the truck is times a period of vibration of the source. And so we're going to say that the shortened wavelength is equal to the original wavelength minus the velocity of the source times a period of vibration. Okay, and so then all that is to say that this new wavelength is shorter. Now, a notation thing. You're going to see in the final products here that there's going to be a VS and there's going to be a V. And it's easy to get those mixed up because there's source and there's sound, and they both start with S, unfortunately. The one that's marked with the S subscript will always be the source, and the one that's without a subscript is going to be the sound. That sort of makes sense. The speed of sound is not a constant, but it is constant for the same temperature of air. And so the source could have all different ones, different velocities, and that's why you have to designate the VS, versus the sound is fairly constant in a certain situation, and so it doesn't have a subscript, maybe doesn't need a subscript. Now look, we're saying that the frequency is the wave speed divided by the wavelength. We know that from the wave speed equation. And so now this altered wavelength is the original wavelength minus the velocity of the source times the period. And so putting in the original wavelength was the wave speed divided by the original source's frequency, and the frequency and the period are reciprocals of each other. We can get two things in the denominator that both have frequency of source in it. And so it's in the denominator of the denominator, so it becomes in the numerator when it factors out. And so you get this handy thing, that the frequency observed is the frequency that was produced, frequency of source, times a fraction that is going to be more than 1. You can see that this fraction right here, the velocity of the source divided by the velocity of the sound, well, a lot of times that comes out to be less than 1. So I'm going to show you a case when it's not less than 1, but the velocity of the source is going to divided by the velocity of the sound will be something. And if I do 1 minus something, I have a denominator that's less than 1. And if I do 1 minus something less than 1, I get more than 1. Now, a similar thing could come about by looking at an observer that was behind the source. Now, I don't want to spend the time in the video, and so you could think about that yourself and see that the wavelength is going to be longer by that same factor that the wavelength was just shorter. And so it will give you a similar thing. It's just that now I have a plus sign in the denominator instead of a minus. Now, there's a similar situation, but slightly different whenever it's the observer that's moving. So say we had this stationary speaker, and this observer was encountering the waves. Now, the wavelength perceived is going to be a little shorter, not because it actually is shorter, but because this person's ear is hitting wave crests more, or wave compressions more frequently than he should be if he were just standing still. And so you can talk about that the frequency that you observe is the frequency that was produced plus the velocity of the observer divided by the wavelength. This is basically saying what's the frequency, the extra frequency you're getting because you're moving. And it gives you a similar thing, but not exactly the same. And it would be neat for you to try in the example coming up to see, well, what if the source were moving, or what if the observer were moving? And then we can say that there's another situation whenever the observer is moving away. So it's nice to have these on a note card. It's nice to have these on your notebook whenever you're doing your problems, and you could say, okay, this is a situation where the observer's moving, the source is moving towards, moving away. Here's an example for us. We have a loudspeaker in a car, and it's producing a frequency that is 20,510 hertz. Now, if you watch the last videos on hearing, you know that 20,510 is beyond the range of human hearing. And so you're not going to hear this. But it says a healthy young person with normal hearing is standing nearby on the sidewalk and cannot hear the sound. Of course they can. Now, when the car is moving, the person can hear the sound. Why? Well, that sound could be Doppler shifted, and so that sound could actually be shifted into the human range of hearing. Now, they first ask, is the car moving toward or away from the person? Well, if it's moving toward, the picture is going to look like that with this real short wavelength with this real high frequency, higher than it's even supposed to be. You're never going to hear that. This is higher than too high. It's higher than 20,510. You're never going to hear that. But in the back, yeah, maybe you could hear that if it's moving fast enough. Here, the frequency is small enough. And we're going to say maybe this observed frequency is down to 20,000 hertz. And if that's the case, then you'd at least have a chance of hearing it. A lot of people can't, but at least you'd have a chance. Okay, so now, they say if the speed of sound is 343, what's the maximum speed for the moving car? So we have a moving source, and it's moving away. And so moving source, moving away is going to be observed frequency is frequency of source times 1 over 1 plus velocity of source divided by velocity of sound. Now, I'm going to rearrange that, and I actually rearranged that before I started the video to preserve the time a little bit. And so you can stop the video, and you can see if you can get to the point where we say that the velocity of the source is the velocity times the frequency of the source divided by the frequency observed minus 1. So again, stop the video and see if you can go from that equation that I have circled above, to this one. Okay. Now, if I just go ahead and plug in the velocity of the source, or solve for the velocity of source, that is, and put in the velocity of the sound, the 343, and for the observed sound, 20,000 hertz for the frequency, and the source, that 20,510, you will see this is moving at 8.75 meters per second, which is very realistic for a car. Now I'm back on the live simulator, and this time I'm going to do, instead of letting the source move at a fraction of the speed of the sound, I'm going to let it move at the speed of sound. And so you can see my fraction up there is telling me what percentage of the speed of sound. I'm at 89%. I'm going to see if I can get it right on 100%. I've done it. And so now do you see what's happening here? Now the plane and the sound are moving at the same speed. So the sound cannot get ahead of the plane right there. Remember, what you're seeing here, these are compressions. And so every place you see a purple ring, that is a place where that's not 1 atmosphere of pressure. It's something higher than 1 atmosphere of pressure, depending on how loud the sound is. Well, right here, you've got a ton of constructive interference. That is a place where we've got compression and compression and compression lining up on top of each other. This is air that's so dense. For a long time, humans thought, well, that's a barrier, that's a sound barrier, and there's no way we could get through that. Turns out that if you make the plane aerodynamic enough and the plane powerful enough, you can blast through that sound barrier, and that is called breaking the sound barrier. You can see here, this is what you have whenever you're moving at the same speed of sound. The simulator also lets you go beyond the speed of sound. That number that you're seeing up there at the top, that fraction of the speed of sound that the plane is, they call it the Mach number. And the Mach number is just that, the number of times faster you're moving than sound. Maybe this is Mach 2. If I can get it right on 2. And you can see now, since you're moving twice as fast as the sound, as soon as you make a sound, you pass it and you leave it behind. Okay. So as I say, some interesting things do happen as you go faster and faster and start to get a speed that's appreciable compared to the speed of sound. You can see here that when you're at Mach 0, and as I said with the simulator, this Mach number is the number of times greater the speed of the source is compared to the speed of the sound. Or it's possible to have a Mach of a fraction. Hardly anyone ever says that, but you could have a source that is not moving as fast. A picture for Mach 0 would be what we started with. A picture for Mach 0.5 would be what we started with too, with a little bit of Doppler effect going on. Now Mach 1, there's not going to be any progress between the wavefront and the plane. And with Mach 2, now as soon as you produce a wave, you are actually already past it. And these all have applications. And so we have, with a plane, that sound that's behind the plane, it forms a conical wave. And we call that conical wave front a shock wave. This area right here is going to be really, really loud sound. And if you happen to be standing down here on the ground, you'd be surprised that you wouldn't hear anything. See, the sound hasn't gotten to this part yet. But this person will hear a really intense loud sound, and we call that experience a sonic boom. Since that's high pressure, if this is happening over in a really humid environment like fighter jets often fly in, then you might even see a cloud form because of how high the pressure is at that spot. You'll also see this with two-dimensionally with something that's moving across the surface of the water, like a duck. You can see that these ducks are producing waves that are shaped like triangles like that. It's a two-dimensional version of what you just saw. We call those bow waves because they come off of the bow of a ship. And remember, what was the problem with the boxing gym that only had one punching bag? You had to wait for the punchline.